welcome to the Explainer. Today we're diving into one of the absolute biggest paradigm shifts in modern AI scaling. We're going to answer one seriously astonishing question. How exactly can an AI with hundreds of billions of parameters use only a tiny fraction of them and still produce world-class results? For years, the whole story of AI has just been about building bigger and bigger brains. But what we're actually finding now is that the most advanced models are learning to use only the specific parts of their brain they really need at any given moment.
Okay, let's put this into perspective by looking at the sheer scale of the crisis we've been facing. 1.2 trillion, that was the total parameter count of Google's GLAM model, which, to give you an idea, was roughly 7 times larger than GPT-3. The AI industry has just seen this explosive growth, scaling models from millions to billions to literally hundreds of billions of parameters. But that scaling, it pushed us right up against a physical limit. We hit massive memory and power walls. Pushing every single piece of data through every single parameter of a trillion parameter model consumes so much electricity and generates so much heat that we were threatening to just blow right past the thermal design limits of our silicon hardware.
So it really begs the question, right? To understand this unsustainable cost of dense computation, we have to ask, if having more parameters makes an AI smarter, why not just brute force it? Use every parameter for every word. Well, imagine a massive factory. Every single worker on the floor has to touch every single product coming down the assembly line, regardless of whether they even have the right skills for it. That is exactly what a traditional, dense AI model does. Even if a simple math problem only needs a few specific logic parameters, the entire trillion-parameter network fires up. It's frankly an incredible waste of time, money, and energy.
Chapter 2. A radical new idea. The paradigm shift to sparse computation.
To get away from that brute force factory setup, the industry desperately needed a paradigm shift. They realized that to keep scaling up, we needed systems where computation isn't just massive, but actually intelligent and selective. So the core of this shift is the contrast between these two architectures. On one side, we've got dense models. They process all data uniformly. Sure, they're predictable, but they suffer from this inherent inefficiency because they're processing huge amounts of redundant data. It's kind of like multiplying by zero over and over again. On the flip side, we have sparse models. These are dynamic. They only engage computational resources based on what data actually matters. By entirely skipping zero or low-value parameters, sparse models drastically shrink the active memory footprint and dynamic power consumption. And the most prominent, incredibly powerful form of this sparse architecture today is called mixture of experts, or MO. Think about it like a hospital. Instead of having every single doctor in the building examine you for a sprained ankle, you go to a triage nurse, and they route you directly to the specific specialist you actually need. In an MOE model, the neural network is chopped up into smaller, highly specialized subnetworks called experts, and sitting right in front of them is a gating network, our triage nurse, that decides exactly which expert is the absolute best fit for the incoming data. Chapter 3. Following one token, the microjourney. Let's zoom way in on a single piece of data navigating this complex network, just so we can see sparse computation in action. It's actually a lot like an airport efficiently routing passengers to the correct gates. Step 1, the token arrives at the layer. Step 2, it hits the router, or the gate network. This router runs the numbers, calculating probabilities using a softmax function to figure out which experts are the best match. Step 3 is the top K expert selection. K is really just a variable. Often it's just 1 or 2. The router picks, say, the top 2 experts, sends the token down those specific pathways in parallel, and completely ignores the rest of the network. Finally, in step 4, the outputs from those selected experts are merged back together and passed on to the next layer. And here is the truly mind-blowing result of that whole routing process. 8%. By only selecting the top few experts, a massive 1.2 trillion parameter model, like the GLAM model we were just talking about, might only activate a tiny fraction of its network for any given word. In GLAM's case, it only activated about 96.6 billion parameters per token. That means 92% of the model is sitting quietly, drawing minimal power, while the 8% that is actually relevant to your prompt does all the heavy lifting. This is literally how you get the knowledge capacity of a trillion parameters, but with the computational cost of a much, much smaller model.
Chapter 4. Engineering at Scale. The Irregularity Tax.
But look, as with any incredible breakthrough, there's a catch. Moving away from predictable, uniform, dense computation introduces some severe hardware and software bottlenecks. Engineers actually call this the Irregularity Tax. First up, you have load balancing and expert collapse.
What if the router accidentally learns that one expert is slightly better at, well, everything? Suddenly, every single token gets sent to expert A. Expert A gets completely overloaded, while the other experts just sit idle and fail to learn anything. Then you have the physical hardware constraints. Because experts are scattered across different GPUs, routing tokens requires massive communication bandwidth between the chips. The memory access becomes highly irregular and unpredictable, which honestly drives memory controllers crazy.
To prevent the whole system from breaking down, engineers had to introduce some seriously clever mathematical tricks. To solve the load balancing issue, they introduced an auxiliary loss. This basically penalizes the network if it doesn't distribute tokens somewhat evenly. They also added noisy gating, which is literally injecting tiny bits of mathematical noise, so the router is forced to explore different experts instead of playing favorites. And to protect the hardware, they implemented expert capacity limits. If an expert hits its maximum token capacity for a batch, any extra tokens just overflow and are dropped. They get passed to the next layer entirely unprocessed. I know, it sounds brutal, but it's a totally necessary trick to keep trillion-parameter sparse models practical and running smoothly.
Chapter 5. The Future of Sparse Intelligence. Emergent Modularity.
We are now looking at the absolute cutting edge here. Up until recently, experts specialized in low-level stuff, like basic punctuation or simple syntax. But researchers are pushing the boundaries to create what's called emergent modularity, and this recent paper on the EMO model illustrates a massive leap forward. The researchers figured out a way to train the MoE architecture so that it learns modular structures entirely on its own. Without any explicit human labels, out of a pool of 128 experts, the model naturally groups specific experts together to handle coding, another subset to handle web development, and another for biomedical text. The AI is literally organizing its own brain into highly specialized departments.
And here is why that is such a huge deal. Because the EMO model is so perfectly modular, you can actually slice the model apart. Say you want an AI just for a biomedical application, you can extract only the 25% of the experts that are relevant to that field. When you do this with the EMO model, you see only a 1% drop in absolute performance. If you tried to slice up a standard MoE like that, you'd suffer a massive 10% degradation. This means that in the future, you won't need to load a massive monolithic model onto your phone or laptop. You can deploy just a tiny, highly relevant fraction of the AI for your exact specific task.
So let's wrap this all up. These 3 insights really highlight why the future of AI scaling isn't just about building bigger brains, it's about building vastly smarter and more specialized ones. First, sparse models only activate the expertise needed for each token, which saves immense power. Second, the mixture of experts architecture is the key to making 100 billion and trillion parameter models practically deployable. It cuts out the unnecessary brute force computation. And third, the future of AI may depend just as much on intelligent routing and emergent modularity as it does on raw parameter counts.
I want to leave you with this final thought as you consider how fast AI is evolving. As these networks increasingly mirror our own selective cognition, it becomes pretty clear. Perhaps intelligence isn't about knowing everything. Perhaps it's about knowing exactly which expert to ask. Thank you so much for joining me for this explainer. Keep wondering, keep learning, and we'll catch you next time.